the screen? Halo, halo.
Bisa, Pak.
Okay, yeah. So we discuss again today, just like yesterday, about diffraction. So, but we use Rayleigh chapter 36. So we have discussed yesterday about the diffraction and the wave theory of light. So it means that the light can be thought of as a wave here. So this diffraction is the proof that the light have wave properties. Okay. This is the picture of the diffraction of single slit. Yeah. The brightest one is the central maxima, yeah, or the zeroth maxima. Yeah. Well, this is bright, dark, bright. So this bright, this is the secondary maxima. Yeah. Okay. So this is the diffraction pattern produced by a razor blade. Yeah. But we will omit this picture because it is outside the syllabus. So this is also the Fresnel diffraction pattern. Yeah. It is also, we omit this one because we only consider the slit. Yeah. Okay, diffraction by single slit. So we have one-dimensional slit, for example, like this. Okay, with the width A. Okay. So if the incident wave like this passing through this slit, okay, with width A, okay, there we'll have this diffraction pattern. Okay. Okay, this diffraction caused by the phase difference, yeah, between all the light, the path that the light have been taken. Yeah. Okay, so yesterday we have derived the first minimum, yeah, of the single slit diffraction. Okay, like this. So basically, the diffraction is nothing but the combination of infinitesimal interference. Okay. So this, for example, we divide the slit by 4, yeah, something like this. They have the same to each other, have the same path difference. Okay, this one, and we assume that the distance of the screen is very large compared to the width of the slit. Okay, and also what is it? The distance between central maxima, for example, and the first maxima also is larger, yeah, than the distance between central maxima and the first maxima. So everything else taken to be larger, very, very large, yeah, compared to the width of the slit, and also the central maxima, the distance between central maxima and the first maxima. So we could take that this path is parallel to each other, this R1, R2, R3, R4, okay? Because this is very large, the distance of the screen, okay? So we still get this at the screen, the wave becomes planar. Yeah. Okay. So this is the second minimum. Yeah. The second minimum for m equal 2. Okay. So this is minimal dark field for single slit. Okay, then we have also discussed the derivation of the above formula, yeah, about the intensity in the single slit diffraction qualitatively. This phase difference basically is equal to K times delta X sin theta. Okay, delta X is related to this D here in this case. Okay, so this is the picture of sin function. Sin means sin x means sin x per x, sin x over x. Okay, so they have the phasor have the same phase. Okay, and this is in general. Okay, so in general basically is the arc, yeah, of the circle, part of the circle. Okay. So because the diffraction of single slit can be viewed as the combination of and slit interference. Okay, so we will get this EM to be the arc. This one, it's bend. Okay, this E theta here, yeah, is this one, this ER. We have used the different symbol. So we get this equation 3611. Okay, this related. This IM is EM squared. Okay, EM squared. Okay, we have also discussed that phi here is 2 pi over lambda S in theta. Okay, this phi is equal to 2 alpha. Okay, we have, so we omit this material because it is outside the syllabus. But I want to talk about is for resolvability. It means that resolve means we could split. Okay, we could split the source. Yeah. The source of the light, the incident light. Okay, this is, for example, which one is the picture? Just a moment. Okay. So, for example, this one, two source coincide, and this is two source become away from each other, and they're also away from each other. Okay. So they have this resolve. Resolve means that the first maxima somehow split. Yeah. Split because it's they are coming from the source, right? This maximum, this maxima, each maximum, this one. Okay. So somehow this so-called Rayleigh Criterion. So we have that this angular separation of this the diffraction is theta r. This sin theta r is equal 1.22 lambda over d. Okay. So because the angles are very small, so we could take the sin theta r is approximately equal to r. Okay. So this is diffraction by double slit. So the first picture describe purely interference. Okay, this one. So we omit the width of the slit. Okay, the width of the slit. Okay, so we get this one. We only consider the distance between two slits. Okay, the figure B here is the diffraction. Okay, diffraction of single slit. Okay, so we have this interference and this is diffraction. So diffraction by double slit, it means that we take the multiplication of the diffraction effects times the interference effects, okay, purely interference effect. Okay, so this is the result, okay, the result of this multiplication. So in the middle, as usual, this is the central maxima. Okay, this is the brightest one, and this is the first and the secondary, next secondary, and so on. Okay. Okay, any question so far? Any question? No. Okay, let us continue. So it means that you see that from this formula, okay, sin alpha, like this, so it means that this alpha becomes minimums at the multiplication of pi, okay? While beta is the multiplication of 2 pi, okay? Sorry, not 2 pi, m pi, okay? So somehow this multiplication become like this. So it's more difficult to get both. Well, we could have, so it is difficult to find the maxima, even for example, the third or the fourth maxima. It is easy to obtain only for minima, the dark interference, yeah. Because dark interference, for example, or the dark diffraction occurs or happen at alpha equals to multiplication of pi, or this beta is the multiplication of m plus half pi, okay, this one. So you took one of them become minimum, then because zero, right? Then since so everything becomes zero times non-zero, it will become zero. Okay, that's why it is easier to obtain the dark interference, the minimum interference. Okay, this is we have discussed yesterday about this diffraction envelope. Okay, this M2 equal to 0 is the central maximum. Okay, this one. And this one is the interference fringe. Okay. So about diffraction grating. So gratings means we have n slit. And slit and slit. So we have so many slits here. Let's say n slits here. And each slit have a distance d. Okay. Like this. So because we have n slits for example, if we take more than 10, okay, the picture of this, for example, an interference diffraction will be like this. Okay, the intensity. This one here, there are some also secondary maxima, but it's really very small compared to the central maxima. This is m equals 0, and this is m equal 1, m equal 2, and so on. Okay, the picture something like this. This is the intensity compared to the theta. Okay, so basically this is the maximum for n slit. We get this one. This is maxima lines. Okay. So what about the width of the lines? So like this, the width of the line is, we call it this delta theta HW, which W is half width, yeah, of this central line. Okay. So the first minimum occurs at this n d sin delta theta HW is equal to lambda. Okay, because this is very small, so basically it will be sin delta theta HW is equal to delta theta HW. Okay, so we will get that is delta theta HW is equal to lambda over ND. Okay, this is the picture of half of that delta theta HW. Okay, so this is for the first minimum. So for maxima, we have this delta theta HW is lambda over ND cos theta. So this theta is related to this theta, okay? This one. So we could also take the derivation of the maximum, the minimum. So this is basically, this is n times d. We have n slits, okay? So this is in total, so this delta theta HW, yeah, is totally for n slits, yeah. Not, so this one, so this theta, for example, for each slits, okay, for this delta theta HW is for all, yeah. Okay. This, the width of this slit is n times d, for example. Okay. So about dispersion, so somehow dispersion is related to the spreading of the wavelength. Yeah? So you see that, for example, this is the dispersion, okay? We have blue, red, orange, green, yellow, yeah, this is the dispersion, okay? Somehow, yeah, the dispersion is the split of the distinguished wavelength, yeah? So we could see red, blue, violet, green, yeah, from the disk. Yeah. So this is the example of dispersion like this, okay? So this is the definition of the dispersion d delta theta over delta lambda. Okay, so because the dispersion here occurs only at the maxima, maxima secondary or next secondary maxima, so we have that this delta theta here should be this one, okay, over delta lambda. So we get that this d, the dispersion of a grating of this n slit is m over d cos theta, where theta is the angle for a single slit. Okay. And then for resolving power, it is also related to the splitting. So the splitting, this R is the lambda average over delta lambda. Okay, what does it mean? This the lambda average, this average of the lambda we consider, okay, over delta lambda. And this R here is n, number of grating, times m. M is the type of this maximum. Any question? Okay. Okay, this is the proof. Okay. So this is the picture of the intensity patterns for light of 2 wavelength sent through the grating, table 31.6. So for example, this is the grating A, the number of the slits is 10,000, B is 20,000, the C is 10,000, okay? And the distance between slits is this one, in nanometer, 2,540. Okay, this theta is the same, this D is the same, but R, is different. Okay, there is the resolve power. Okay, we come to the end about this X-ray diffraction. So basically, the X-ray diffraction is used to uncover, to know, to show the shape of the crystal. So the shape of the crystal, for example, this is for the salt NaCl. We have the ion Na, then also the negative ion Cl minus. They form a crystal, okay? And the crystal, it looks like a cubic, this one. Okay, this picture is the conclusion from the X-ray diffraction. Why we use the X-ray diffraction? So, for example, as we have discussed just now, for example, this one, the distance between two slits, okay, this is the in the order of 2,000, around 1,000 nanometer. So nanometer is 10 to the minus 9 meter. So for 1,000, it should be around 10 to the minus 6 meter. Okay, 1 micrometer. Okay. So the slits, the distance between the slits is one micrometer. Okay. But if we consider, for example, this molecule, this crystal, this salt crystal, okay, the distance between this ion is less than 1 micron, okay? 1 micron. You see less, yeah. So because it's less than 1 micron, we should take the wavelength to be shorter, yeah. It's shorter than the visible light, okay? So we will get, this is the first order maximum of the Bragg, we call it the Bragg formula of X-ray diffraction. This formula coming from the experiment, okay? It's similar for interference, so for this maximum interference, okay? But this formula coming from the experiment, okay? As you see that, if we assume, for example, lambda is equal to 1 angstrom. 1 angstrom is 10 to the minus 10 meter. Okay, and the distance between two slits, for example, 3000 nanometer. Okay, so the first order maximum occurs at this angle. Okay, it's very small. Okay, it's very small. Okay, so we cannot use visible light, we cannot use this visible light to know how the shape of the crystal. Okay, so somehow, because the distance of this crystal ion is around this lambda, around this 10 to the minus 10 meter. Okay, so we should use the wavelength in which is this wavelength is the light is around this wavelength, and this is exactly the X-ray wavelength. Okay. So that's why the X-ray diffraction, we could determine D here. D is the distance between two ions, okay, or the distance between two atoms, something like that. So this is why we this diffraction, okay. This is reflection, okay, and this also reflection, but they have different distance, different paths, okay. So this different path cause the different phase, okay. That's why we have interference or diffraction. So this is the Bragg law. Yeah, this is this formula coming from the experiment. This is 2D sin theta m lambda. This is the criterion for intensity maxima for the X-ray diffraction. Okay. And this Bragg, this Williams Bragg here, and also his father also shared the Nobel Prize in 1915 for physics. Yeah. I think this Wilhelm Bragg is the youngest Nobel laureates in physics, or in Nobel laureates in physics. Yeah. I think he's 25 years old at that time. Okay, that's, I think, this summary and review. This is about diffraction. Is there any question about this? Any question?
Sir, can I ask?
Yes, please.
For the single slit diffraction formula, there's I and IM. What's the difference?
Single diffraction, okay. There is a.
I mean double slit, I think. Wait.
Double slit. For double slit, you mean?
Yes.
This
For
one?
the intensity.
Oh, this IM.
Yeah, what is
IM
IM?
is maximum intensity. This is EM squared. EM is the amplitude. This I here, it depend on theta. This one. This D here is the distance between two slits, while A is the width of the slits, of a slit. Is that your question, or?
Yes, is my question.
Okay. Is there any question? Again? Okay, maybe you have to again take some problem. Yeah? Okay, can you walk, all of you, walk on this number 12? Yeah? This number 12, just number 12. Okay. So I will give you until 12 o'clock, I think. Yeah. For assignment. Okay. Number 12, yeah. You could also open your book, page 1016. Yeah. Oh, sorry, it's 1015. Sorry, it's one page before. 1015, number 12.
Sir,
Yes,
for the deadline, what's the deadline?
today is 12 o'clock.
Uh,
Sorry, 13 o'clock, yeah, sorry.
Oh, okay. Thank you.
Okay. Sorry. Okay. Sorry. Okay. I will, okay. Not 12 o'clock, yeah, sorry. 13 o'clock, sorry. Okay, done. Update, okay. 1 o'clock, yeah, the deadline, sorry. Okay. don't forget don't forget to checklist ya your attendance ya at 1 o'clock. Can I stop share? Okay. Okay, stop share ya. I stop share. You could open also your book.